And actually, before I take over, I'll have Rob introduce the talk. And so, yeah, Rob, do you want to introduce yourself, and then I'll start showing the slides.
Sure. Yeah, Robert here, also from the Orbio Earth team, yeah, started Orbio around 4.5 years ago, and really excited to present some of our work today. And yeah, really excited about this moment. There's a lot of work that led up to this moment today, so really excited to give this some light of the day. And yeah, I'm gonna kick off. Basically, this is as Claire was mentioning, for us, our project that we called an open source version of our work at Orbio Earth, which we called Project Eucalyptus. And essentially, we imagined this to be an open source toolkit for satellite-based methane detection and quantification. And we're gonna share more detail in this talk what this is about and what that entails. But first, next slide, please. I want to take a quick second to give condolences to a beautiful human that passed away last week, Manfredi, the head of IMEO, and the Mars program sadly passed away. And we are very grateful for all his contributions to this space. And I think we all wouldn't be here in this format today without the IMEO and his amazing contributions. And so I want to take 30 seconds at the beginning of this talk to just be in silence and with his family and loved ones. Okay, thank you so much for joining. Could you go on the next slide, please, Maxime? Okay, what does this talk about? So essentially, we have like 4 key goals that we want to achieve today. One is that we want to tell you guys, the community, and everybody else outside there about our newly open source code and models for methane detection. So we want to present you what Project Eucalyptus means and how to work with it and how to access it. We want to basically give a couple like shout outs or a couple realizations we made and like dive deeper into a couple of single points. One of them is why computer vision suits this specific problem and why this is a good route to tackle the methane emissions detection and quantification problem. Secondly, we want to go a bit deeper into synthetic data generation. There's been a lot of amazing work done in this space by some people that are also present in this call today, and want to like just go a bit deeper into our experiences with this sort of approach. And then thirdly, we want to talk a bit deeper about detection threshold estimation. It's a hot talk since a couple of years, the classic question, what's the detection threshold? And we want to give a bit deeper into what our take on this space is at the moment. And then thirdly, very clearly, this is us to tempt you to read more in our online documentation. There's a lot of stuff we put out. And so we just want to make it a bit exciting for you guys to go dig deeper on yourself and by yourself. And then really, like any open source project, we really want this to be a baseline to start discussion, get feedback, spark ideas, and really make this a bit of a baseline to accelerate innovation from here. Quickly on us, who do we mean when we talk about us? We're a team of 14 people today here at Orbio, and massive contributions to this project were done by Timothy Davis, Robert Edwards, Zani Foy, Jack Angela, myself, Thomas Edwards, Diaz Sillers, Vikram Singh, Wojtek Adamczyk, Maria Navarrete, Maru Gniazzi, Philip Popin, and Maxime Rischard. Great. One massive question that I've gotten a couple of times in the last 24 hours, why did we put all this open source? And I think it's very simple. If you go further one slide, the answer is actually in one simple graph, which is this one. It's from Evans and the rest of the Stanford team, or like former Stanford team, or basically their work from 2023 and 2024, a single blind test of 9 methane sensing satellite systems from 3 continents. They basically single blind tested a bunch of this methane work. And what we can see on this diagram, without going into depth into any of this, but basically what we can see is some of the known issues of satellite derived methane estimates is things around massive error bars in quantification. We see false negatives, like emissions that are missed. We see false positives, not in that study, but in the more recent one, there's some examples of that. And so there's the sort of known issues of satellite-derived methane emissions and quantifications, but there's also one other important angle of this diagram, which is you actually have a very strong divergence of models. The exact same input data analyzed by different models, by different teams, by different providers, by different systems, basically leads to completely different estimates of and completely different outputs in terms of quantification, in terms of detection or no detection. And essentially the key problem of all of this is that over the last couple of years, and we've seen that while we have came into this space and developed into this space, is that we basically seeing an increase in distrust in decision makers that are relying and want to use this data to make decisions. And here we're talking about potentially the oil and gas operators, we talk about regulators, we talk about investors, people that make ground decisions based on this data. And we're seeing an increase in distrust because company A or vendor A or NGO A tells them emission estimate is X, and then somebody else tells them Y, and then they look at the ground data and they don't understand the world anymore. And this trust and confusion, which is partly rooted in massive differences in how models are created and how like models are assessed, is leading to actually satellite-derived methane emissions estimates being used less frequently, and leading to less of the impact that this data can actually have in this world. And so that's one step of why we are open sourcing this, is we want to actually accelerate a lot of the discussions and important work that are going on from like entities like NIST around thinking about how can we actually converge models, how can we actually accelerate towards finding what the truth is here, what are the best possible approaches, and actually mitigating some of that distrust that is creeping into the sector.
Okay, this is where I take over. So what are we open sourcing exactly? Actually, quite a lot of things. We're publishing some model weights for a computer vision model that does methane detection for Sentinel-2, Landsat 8, and EMIT. It's all in a single, all of this is in a single GitHub repository. The link has been shared on the email list, but I'll also share it at the end of the slides. So we're sharing the actual models. We've got a few kind of demo notebooks showing kind of end-to-end reproducible steps to do inference, to create synthetic data, and a few other kind of critical steps in the pipeline, post-processing, quantification. We've got a toolkit for how to simulate plumes and the synthetic insertion of plumes in remote sensing data in satellite imagery. So a lot of kind of demos, tools, code. And then alongside that, we've also got extensive documentation in the form of a queue of questions and answers that give background, insights, some deep insights, some random insights, some theory, a bit of physics, some good ideas, some bad ideas, some of the results, lots of examples of things, also some of the remaining problems, limitations of these models, and some of the next steps that we want to work on. So it's this kind of really kind of rich document. I'll just show you for a second. It looks like this. We've got different sections on the training data, on the physics, the radiative transfer model that we use, the computer vision model itself, explaining like what loss function are we using, lots of different kind of questions, some of them high level, some of them really technical for the very technical people. And the idea of doing it as a Q&A is to allow people to just quickly browse and only read the things that they're interested in for whatever use case they have for this information. So some people will want to go in depth and they can read it all. Some people just want a high level overview and they can just read the questions that interest them. And then we've actually got then a code archive of entire R&D pipeline, including training data generation, the actual training script that we use to train a neural network, of our kind of test metrics, validation pipelines. It's just a kind of archive of our code as it is, as we use it at Orbio. It's not really kind of necessarily user friendly. There's a lot of documentation in there as well, but it's not meant to be like you can go and immediately start using this code. It's more intended for just transparency and for browsing for people who are maybe writing similar code to be able to go have a look and see like, well, let's see how they've done it. And if there's any question that we haven't really answered in the documentation, because there's so many nitty-gritty details when you do something like this, you can just go and look at the code and find the answer for yourself. So there's some nice kind of curated notebooks on one hand, but also just an overall kind of code archive as well for kind of full transparency. And those two things together, along with the documentation, gives a kind of full overview of everything we've done, how it works, how to use it, how to take it further. All of this we're publishing under a non-commercial license, so it's completely free to use for research and non-profit purposes. And but I think, Rob, I think we're saying if you're interested in using some of this in a kind of commercial setting, we're also open to discussions about that. Just contact us, and that's not necessarily something we would say no to, but the license a priori is non-commercial and for research and non-profit. So yeah, there's a lot there, and but what I'll do now is just kind of dive a little bit into the work that we've done, give a few kind of vignettes of some of the thinking, some of the ideas we've had, some of the things we've done that are new ideas. And it's meant to be a bit of a teaser to encourage people to go and dig deeper, look at the code, look at the documentation, and also maybe kind of elicit a discussion and questions. So hopefully leave lots of time for questions at the end. That's my hope. But yeah, so just to say a bit about the scientific journey that we've taken, we really took a turn towards computer vision pretty much exactly 2 years ago now, because the Orbio journey started before that with the more kind of, you could call it more classical methods, developed by Daniel Veyron and his friends at Harvard, who developed the kind of remote sensing methodologies for multispectral data in particular, and we're particularly interested in Sentinel-2 for methane detection. We call these the kind of classical method, and initially what Orbio worked on is a way to scale these up and improve on them. So we had several proprietary improvements to reduce the signal to noise using some tricks and filters and a bit of principal component analysis and this sort of stuff. But then, so 2 years ago, we came to realization that this classical algorithm made actually quite limited use of the available information. And so, yeah, kind of, I wanted to explain this because we're not just doing computer vision because like neural networks are cool and powerful and let's just try a neural network, but we had a kind of reasoning for why we thought on this particular problem a neural network would do well. And it's what's shown here on the right. So basically we kind of, if you think about all the information that's available in remote sensing data, and with Sentinel-2, we use the image on the actual target date, but also reference date for comparison. So there's spectral information, and that includes the bands that are in the methane absorbing part of the spectrum. Those are the ones that are being used by the classical methods. but also the bands that are outside of that, the bands that are not affected by methane, but are nonetheless really useful to filter out false positives in particular, to actually better understand the scene. Those are ignored by the classical algorithm. There's temporal information, the use of reference scenes, which is definitely, that box is definitely ticked by the classical methods. But a neural network can do a lot more. It can understand change patterns, vegetation cycles. It can look at, understand how things change in time and use that to adjust its detection. There's spatial information, so spectral, temporal, spatial. There's contextual information from the overall scene, but also the spatial information, the spatial smoothness itself of a methane plume. Again, that's something that's not really utilized by the classical methods. It's kind of pixel by pixel. And my background is in spatial statistics, so that seemed very kind of clear to me that had to be informative, the spatial smoothness and the spatial information. And then slightly related is morphological information, the shape of the plumes. So that's plumes have certain typical shapes that are informative, but actually maybe even more importantly, the typical shapes of the things that cause false positives, like agricultural fields, rectangular irrigation circles, like a big circle that you get, rows, these kind of very linear features. That's very useful morphological information that a neural network can access and use. There's information about land cover, etc. So we kind of looked at this and realized like there's a lot of information that we're not using right now that is very powerful. And we saw two rows in front of us. One was to develop additional heuristics and filters for the classical algorithms to do things like look for information in the RGB bands, look for similar shapes to filter out false positives, all sorts of tricks and kind of techniques that we could use, or just take the neural network approach, the computer vision approach, the modern computer vision approach, and just generate training data and let a neural network figure this out for us. And it is very clear, just thinking of it this way, it was very clear that this would be a really fruitful application of neural networks. So we made that choice. So we kind of pivoted scientifically to that use. And so let me talk a little bit about exactly what the computer vision task is, what we're doing. So the training data is the most important part really here, because we're in a domain where there's pretty much no ground truth data. And by ground truth data, I mean an actual map of methane concentrations for real plume observed by Sentinel-2 or any other satellite. That basically doesn't exist. Right? The closest thing we have would be the controlled releases that are being done by Evan's team and a few others, where we know the emission rate and maybe the wind direction, but we still don't know where the plume is, the pixel by pixel concentration. It's not something that we can train a computer vision algorithm on. So we're in this kind of crazy domain where we want to do computer vision, but there's absolutely no ground truth data. But what saves us is that it's relatively easy to generate synthetic data, because the atmospheric physics of absorption of light due to methane is easy to emulate. So we can take a plume, stick it into an image, and emulate the effect it has on the methane absorbing bands, and that can be used as training data. This is not this. I mean, this was a kind of new idea maybe 2 years ago when we kind of starting, but I think this is not a new idea now. There's a few kind of publications now that are using this approach as well, and I think it's definitely the way to go. It's a very powerful approach because you can just generate training data as large as you want, which is an amazing luxury in deep learning. And for the predictors, the features, the inputs into the neural networks, we use a selection of bands, so the methane absorbing bands, and then also the non-methane absorbing bands from the target scene, and then also from a reference scene. And then additionally, we added a second reference scene. So there's T-1, and also T-2. The idea is the neural network can better understand change patterns over time. But all of these bands are undifferentiated. They're just inputs into a neural network, we use a UNet, which is a very classical computer vision architecture, and it just gets these 30 or something bands as undifferentiated inputs. And then the ground truth in square quotes, because it's not actually ground truth, it's a synthetic ground truth. At Orbio, we use this band ratio, the band 12 over band 11, the ratio of the two shortwave infrared bands, and the fractional reduction in that band ratio. Equally, you could use a fractional reduction in just one of the bands or all sorts of things, but it's the idea is the target, the labels, the ground truth is something that is a proxy for the methane concentration that is directly defined on the reflectances on the bands. And that's the setup. But then one of the most interesting bits for what we did at Orbio is our choice of loss function and how we looked at this problem. Because you can use computer vision and neural networks in a variety of different ways. You could do a pixel-wise classification, where for each pixel you're trying to predict, is there methane here, yes or no? Or you can do a pixel-wise regression, where so that classification is what's called a segmentation task in the computer vision world. Or you can do a pixel-wise regression, where you're trying to actually predict not just is it methane, yes or no, but how much, what is the concentration? And so there's going to be a bunch of zeros, and then you get some concentration or some kind of band ratio value like this. And we actually, and most of the literature does segmentation, so pixel-wise classification. So we decided to do both classification and regression, because for use case, to be able to actually quantify the amount of methane present, we needed to know, is there methane, but also how much? So we got this loss function. It's basically a kind of multitask neural network that has a classification loss component, and then some kind of weight parameter, and then a mean squared error as well on the concentration, but just only defined on the methane pixels. And so it's basically a single neural network that gives us the answer to both questions. Is there methane, yes or no? And then if there's methane, then how much? And one little side, I'm a statistician by background, so a little nerdy aside, you can actually interpret this as the likelihood of a zero inflated Gaussian distribution. And that's actually a very powerful way of thinking about it. That explains why this actually makes sense. And so the output of the neural network then gives you also these two things. It gives you a binary probability kind of mask, kind of likelihood mask for each pixel. Is there methane, yes or no? The example I'm showing here, by the way, is from one of the recent controlled releases on the 19th of November. This was a controlled release at 380 kilograms per hour. And this is the output from our neural network, from a computer vision model. So the output, you get a probability mask, and then you get also a retrieval. Well, you get a band ratio absorption, which you can convert into a retrieval in moles per meter squared in this case. So this is in units of moles per meter squared. And the conditional retrieval, it's the answer to the question, if there's methane in this pixel, then how much? So it's full of false positives, as well as actual methane. It's got lots of little like artifacts all over the place. It can even have negative values in it sometimes, because it's answering this conditional question. But if you combine the answer to the question, is there methane, and then how much, if you multiply these two, you get this marginal retrieval, which looks a bit more familiar to the classical algorithm, which is this kind of the expected concentration of methane, a kind of map of the concentration. And we've got a lot more about kind of background on this if people are interested in this way of doing this, about how the model should be interpreted, how we've constructed this, also in our documentation. To show you another example, this is the kind of prototypical example used in all of the papers on Sentinel-2 methane detection. So this is first a figure from the Veyron 2020 paper, where they developed these kind of classical algorithms for methane detection. These are the 3 different algorithms, and this is the plume, very large plume that they detected in Algeria. And you can see that the classical algorithms, they've got all of these little artifacts. You can see there's a little ridge here where they've got these little pockets of red that for an automated algorithm could easily be interpreted as a plume. You can see a bit of the terrain. You can see this road here where, again, you might expect an automated algorithm would find a few plumes in there as well, and you'd have to filter those out somehow. And the output of the computer vision algorithm is a lot cleaner. You get this likelihood score again, same thing, the conditional prediction. This one is a weird one. There's some negative values up here, but it doesn't matter because when you multiply it, this marginal prediction, you get a very clean detection of the plume with basically hardly any false positives. And so, yeah, this is one of the kind of innovations that we did to have these neural networks that are multitask, and because we really need we need to do quantification, so we need our neural network to also tell us how much methane is present. It's not just a classification problem. Okay, so I want to say a little bit more about our training data, because this is also very interesting, because we talked about inserting plumes into Sentinel-2 granule scenes. I haven't said anything about what kind of plumes, and that's actually a really interesting question with pretty deep implications. And actually, when we started this project, we started with a really unorthodox approach, I would say, which was the idea of what we called recycled plumes. And what we did is that we literally took unfiltered detections from the classical algorithms, which we masked, segmented into individual plumes. And a vast majority, we were processing vast amounts of Sentinel-2 data. And I took the completely unfiltered outputs without any of our tricks to eliminate false positives. I took all of these candidate plumes and I just treated those as ground truth plumes and inserted them into Sentinel-2 scenes. And so our ground truth in this case, then the synthetic ground truth, is full of false positives. It's full of these kind of weird shapes that are definitely not plumes, where you know, this might be a field, this might be I don't know, this might be a little water body or something. There might be some methane in there, but I would say the vast majority of them are false positives. And that was actually deliberate. And there's actually, it sounds like a really dumb thing to do, to train on false positives for a model that you're hoping will eliminate false positives. But it actually has some real advantages to do that. The disadvantage is the obvious one, right? That you're missing out on information from the plume morphology. Because your model is trained on things that are not plumes, so your model doesn't get to learn what the shape of a plume, a typical shape of a plume, looks like. But there's still a lot of other information, right? All the spectral information, temporal, spatial, all of that is still available. Just this is just a one little piece of information here, the plume shape, the morphology that you're missing out on. But it turns out there's still a lot, and this model still performs very, very well, surprisingly well. Even though this is a kind of very unorthodox thing to do. Whenever I talked to computer vision experts and told them I was doing this, they just couldn't wrap their heads around it. It just didn't make any sense to them. They found it kind of offensive that you would train a model on false positives and hope it would then not have no false positives at the output. But so on the Hassi Messaoud example, it does a fantastic job just with this model trained on false positives. It still does a fantastic job detecting the methane and with no false positives. But Hassi Messaoud is the classic example because it's a very easy example. There's a very strong signal to noise. You can actually see it by the naked eye in the band ratio. If you do something a bit harder, this was one of the controlled releases from 3 years ago. Now this was a controlled release at 1.6 tons per hour, so it's still, not that small. And here you can see there's a kind of shadow of a detection, a very, very weak detection. So it's getting something, but it's not at all confident. It's a very weak detection. And actually there's a little false positive here that's actually stronger in terms of probability. So it's kind of going in the right direction, but it is struggling. So why would you want to do this? I'll come back to this. The advantage of doing this is actually that the information about plume morphology is not used. I suppose the disadvantage and the advantage, and I'll explain why that can also be an advantage in a second. But first, let's look at a model with morphological information. So here we tried a different experiment. We took some plumes extracted from Aviris data. So this is a NASA hyperspectral instrument. The data is available in the kind of NASA portals. You can apply a match filter to it. There's a high signal to noise ratio, so you can do segmentation. You can get a corpus of plumes, a few thousand plumes, and that's plenty enough. We take these plumes, we rescale them. By rescale them, I mean we multiply the concentration to the range that where they would be detectable in Sentinel-2. So typically we boost them by a factor of 5 or something like that. We reproject them to be at the Sentinel-2 resolution, and then we insert them synthetically. We do the physics, the radiative transfer physics, and we insert them into methane-free Sentinel-2 tiles. And that's our training data. And so this model now has the morphological information about what a plume looks like, and it does in fact perform significantly better. So I'm showing the same example here. So this is Hassi Messaoud. Again, easy, it gets it 100%, no problem. Actually sees a bit more here in the tail. If you look closely, this one, it tapers out, and now it goes a bit further. But anyway, but all of our models can detect this event. But looking at this more difficult example now, this controlled release from 2022, it nails this one where you see a very strong plume bang in the middle. It's not complete. There's a few kind of shadows elsewhere as well, so it's not completely clean retrieval. But once you take the binary prediction and the conditional retrieval and multiply them, you do get a very clear, clean image of this plume. And so so we do get, with this additional information from the plume morphology, we do get much better detection of the controlled releases. So let's take then, but one limitation of this is that there's only a few thousand of those, and there's biases. We're worried that there would be biases in the distribution of these plumes from the match filter and from the segmentation algorithm that is used, any kind of selection that is done that could bias towards larger plumes or anything like that. So we decided to also try simulating plumes from scratch. And we developed a kind of a cheerful in-house Gaussian puff model. These are recent experiments, which I'll describe. And in fact, I saw on the Meta newsletter, there was a paper on Gaussian puffs model that was published recently that looked really interesting. So this is topical. So we got it's just a very simple two-dimensional puff model, which means that the nice thing with these puff models is that you can have the wind field can change direction and speed, and we use some real wind field data. In fact, we're prototyping this with data from the single blind release. It's got some beautiful wind data in there, so we thought let's just use that. So it's sampled every 5 seconds, and so we use that to create these little puffs that can move with the wind. So it creates these more realistic plume shapes, and we also added a turbulence process just to create these more realistic shapes. Just add a bit of noise. So here's the Gaussian puff without the turbulence, and then we distort it a little bit with this Ornstein-Uhlenbeck process. And for our purposes, it doesn't need to be physically realistic. It just needs to be visually realistic, if that makes sense. It just needs to look like a plume for the purpose of a computer vision algorithm. There's always the risk that with an approximation like this, we introduce some kind of bias and it doesn't generalize. So that's why it's worth working a bit to make them more realistic looking. But there's a lot of advantages to this as well. We can generate, it takes literally 1 second on a completely normal CPU machine to generate one of these plumes. Just wrote a bit of Python and it takes 1 second. So we can generate tens of thousands of these very cheaply. We can perfectly control the number, the size of them. You can control the wind direction. You know the exact position of the source because you've simulated it. So this opens up a lot of applications for training neural network, also for a lot of other downstream applications. It's very useful to have simulated data. And it also works quite well. Again, we get a very confident detection that Hasim Rischard. That's an easy example. And here you can see on that same example in 2022, we get an even stronger detection. We get this beautiful, nice kind of wedge shape here. But, and here's the cautionary tale. I was running this experiment. I was looking at the validation data, and this is from a random model, an intermediary epoch. So it's not even a kind of final model. But I noticed this phenomenon. This is a validation tile where we've actually not inserted any methane. So this is a unmodified methane-free Sentinel-2 granule. And this neural network trained on Gaussian plumes created this inference, this prediction. And then essentially what it did is it basically hallucinated an extremely convincing looking false positive plume. And that's actually dangerous because when we use these algorithms, we have a QA process to assess whether candidate detection is real or not. And it's still very important to go through this QA process. And one of the information that's used is looking at the morphology of this plume and seeing like, does it look physically, does it look convincing as a plume? And so if you have a model that then produces false positives that look like this, extremely realistic shape, it becomes impossible to assess this for a human to assess this by eye and determine. There's no information remaining for the humans to decide if this is real or not. And so this is kind of what I was getting at here with the recycled plume. There's this disadvantage that we're leaving information on the table, but there's also an advantage, which is that because we haven't used the plume morphology to train on, is still available as a sanity check for QA. It's more robust. It's safer in that sense. It's not going to create these super realistic looking false positives. So that's the kind of little advantage of using these recycled plumes. So it's all compromised, and we kind of still evolving all of these methods. But I just wanted to have this kind of cautionary tale here to kind of alert the community that this can happen. And so what I want to talk about next is a little bit about validation. This is also super important. So how do we validate our models? Well, we have got all sorts of internal kind of loss metrics and a slew of other test and validation metrics that we've developed over the years. The other thing we use is known methane sources, and in particular the controlled releases. So I've got a little kind of example here I've extracted from some of the data where, so as an example, so this is for 35 controlled releases, of which 13 there was an actual release, and the rest there was no release. Sorry, I was doing some mental maths. With the recycled plumes model, we can catch 5 of them. When we use the various plumes for training data, we catch 5 more. But when we use the gas and puffs, those experimental models, actually we've got this kind of fractional thing, which means that it was a very faint. Someone typed in 0.25 in the spreadsheet to say like, well, it's sort of there, but it's so faint that probably we would not think this is a real plume. So this is one of the major ways in which we validate our models, and it's wonderful that it's a limited data set, but it's growing thanks to the work that some of the people in this call are doing. So thank you for that. And it's a really useful resource, even kind of internally, to have this kind of ground truth for validation. And then the third way in which we validate and evaluate our models is our estimate of the detection threshold. And that's pretty much the last thing I want to talk about today, as a kind of little vignette of some of the work that we've done. Is how we measure our detection threshold. And the detection threshold, it sounds like a really simple idea, but it's not. It depends on all sorts of things, and especially in our case, it doesn't just depend on things like the scene albedo and soil moisture and the wind conditions, but also something like the reference scene similarity, like how good is your reference scene compared to your target, the data you're interested in. If the vegetation has changed a lot from one day to the next, that makes it a not very useful reference scene. Basically, the kind of temporal stability, if there's been rain, if there's been a big precipitation event between the previous overpass and today's overpass, then it changes things and it's unstable. And again, the reference scene is not very useful. And potentially a bunch of other stuff that only the neural network understands. But we want to be able to make a statement like this. So like near Hassi Messaoud, under a certain wind speed, we can detect plumes with emission rates of 620 kilograms an hour 50% of the time, and 90% of the time we can detect plumes of 1600 kilograms an hour. And that's actually, those numbers actually for one of our models, what we get for Hassi Messaoud. And what I want to do now is explain how we get these numbers and what they mean. But because of this complexity, for first of all, the data from the controlled releases is too small to estimate, and it's just in one or two places. So we can't use that to estimate the detection threshold, we don't think. So we estimate it directly via a simulation study. We make no assumptions about the distribution of emission sizes. We don't do these kind of power laws and see where it tapers off, because I think there's real limitations to doing that. We use synthetic data to estimate directly the detection threshold. We estimated in 3 regions that are meant to be kind of difficulty tiers. There's an easy Algeria tier, there's a medium Permian Basin tier, and there's a hard Marcellus shale. I've got a few slides explaining kind of step by step how we do it, but I'll just give the gist of it in the interest of time. Because basically we can insert a plume, and we use simulated plumes as basically from the work of Gronio and all in 2023. They published a few like large area simulations of plumes, and we use those. We insert them into methane-free granule, and we modulate its strength from like 100 kilograms an hour to 10,000 kilograms an hour. And then we repeat the inference and see, like, as the plume gets stronger, what happens to our detection. And by doing this over a number of different plume shapes, random rotations, random positions, and a whole corpus of locations and dates, we get this kind of population of detections and non-detections. There's more detail here, there's more detail in the docs, but essentially what we can do is we can empirically get the probability of detection for any plume in a certain region, and we get curves that look like this. And one important detail is that for detection threshold to make sense, we have to specify a wind speed, but we also have to specify a rate of false positives. Because with a computer vision algorithm, you can always, because you get a classification likelihood score, you can always detect any plume just by setting the threshold low enough. And so what we decided to do is to define, and this is not necessarily a new idea, but to define the detection threshold against a fixed rate of false positives. And that also makes models more comparable, models that might be calibrated differently, with very different training data. And so with one of our best models at the moment, we get these sorts of numbers where 10% of the time, I've shared some of these numbers already, but you can see for, say, 50% of the time in Algeria, we can detect plumes of 600 kilograms an hour. When you move to the Permian Basin, there's more vegetation, it's a lot more difficult. That goes up to 1,800 kilograms an hour. And in the Marcellus Shale, which is one of our trickiest locations with lots of agriculture, lots of human activity, it's very, very hard. The detection threshold goes up a lot, by 8,500 kilograms an hour. These numbers, they're not directly, I don't think they're directly comparable to other published numbers in the literature. But I wanted to share this. Our approach to how we estimate the detection threshold. And for us, it's primarily a way for us to evaluate models when we train a new model to decide, is this actually a better model, yes or no? Should we put it in production? Should we ship it to our customers, yes or no? So whenever we train a new model, we look at these numbers and we look for low detection thresholds. Okay, thank you so much. I'm going to stop here. But yeah, please go check out our document, our kind of Q&A document. There's lots of kind of additional questions that it answers, lots of detail. Go look at the code, go look at the notebooks. Please engage with it, and if there's questions that are not answered there that you think should be answered there, please feel free to leave comments in the GitHub issues. please feel free to ask additional questions as GitHub issues. We'd love to get also kind of feedback via that. But also right now I've got also a bit of time if people wanted to ask a few questions. And sorry, there's so little time left.